Hey everyone, and welcome. Let's just jump right in. Today, we're tackling a huge concept in coordination chemistry, and listen up because this is a super high-weightage topic for competitive exams like the CUET UG. We're talking all about isomerism.
So let me start you off with a little bit of a mystery. Picture this. You've got two chemical compounds. They have the exact same molecular formula. The same atoms, the same number of each. But one of them is this deep violet color, and the other is reddish violet. How on earth is that possible? It's like they're having a chemical identity crisis, and you know what? We're about to solve it.
And the solution to our little puzzle has a name: isomerism. This is the whole idea that explains how you can take the same set of atoms, but just by arranging them differently, you can get completely separate compounds, each with its own unique personality and properties. It's not about what you have, it's about how you build it. Now, isomerism is split into two big categories. So first up, we've got structural isomers. The key idea to remember here, the one word you got to burn into your brain, is connectivity. For these isomers, the actual way the atoms are bonded to each other is fundamentally different. I love this slide because it just makes the concept click. Think about having a pile of Legos, right? With that same set of blocks, you could build a little car, or you could build a house. You used the exact same pieces, but you ended up with totally different things. And boom, that's structural isomerism in a nutshell. So within this category, we're going to play detective and investigate three main cases. First, we have ionization isomerism, which is all about swapping players in and out of the main group. Then there's linkage, which involves a really tricky kind of ligand. And finally, coordination, which is like a trade deal between two different complex ions. Okay, first case on the docket: ionization isomerism. Check out these two cobalt complexes. They have the exact same atoms, but look closer. In the one on the left, the bromide is a ligand stuck right to the cobalt, and the sulfate is just hanging out as the counterion. But on the right, they've swapped places. Now the sulfate is the ligand, and the bromide is the counterion. So when you put them in water, they give you totally different ions. So for your exam, here's the absolute takeaway. If you're trying to spot this, just scan the formula. Can something inside the coordination sphere, a ligand, swap places with an ion that's outside? If the answer is yes, you've probably found your culprit. All right, let's move on to our next case file. This one is all about a very special character called the ambidentate ligand. Think of this ligand as being kind of two-faced, but in a good way. It can bond to the central metal atom using one of two different donor atoms. It's got options. And this slide just shows it perfectly. Take the nitrite ion, NO2-. It can attach to the metal through its nitrogen atom, which gives you the nitro complex you see on the left. Or it can flip itself around and connect using one of its oxygen atoms, which gives you the nitrito complex on the right. See? Same formula, but a completely different bond is holding it all together. So here's the deal, bottom line for your exam. The second you see a classic ambidentate ligand like NO2- or SCN- in a chemical formula, an alarm bell for linkage isomerism should be going off in your head. Our last type of structural isomerism is coordination isomerism. Now this one's a bit of a special case because it's a two-player game. It only happens in a compound that's made of both a complex cation and a complex anion. And it's all about them swapping their ligands. And I really can't stress this enough. This is the absolute key. You simply cannot have coordination isomerism unless your compound is built from two separate coordination spheres, one that's positive and one that's negative. If you don't have two complexes, it's just impossible. All right, let's switch gears and move to the second major category, stereoisomers. Now you've got to pay close attention here because the rules have changed. With stereoisomers, the atom-to-atom connections are exactly the same. The difference is all about how they're arranged in 3D space. The classic analogy here is just perfect. Go on, look at your hands. They have the same parts, right? Fingers, thumb, palm, they're all connected the same way, but they're mirror images of each other. And you can't perfectly lay your left hand on top of your right one so that they line up. They're different 3D objects. That, right there, is stereoisomerism. A huge type of stereoisomerism is geometrical isomerism, which you probably know as cis-trans isomerism. So in a square planar complex like this platinum one, if the two chloride ligands are right next to each other at a 90-degree angle, we call that the cis isomer.
But if they're clear across from each other, a full 180 degrees apart, that's the transisomer. Same connections, totally different geometry.
So this leads to a really important question that every chemistry student should ask. Is this whole cis-trans thing possible for any molecular shape? And the answer is a big, resounding no. There is one major exception that you absolutely, positively have to know, and that is the tetrahedral shape. Here's the rule to carve in stone. In a tetrahedral complex, all 4 positions are perfectly identical to each other. They're all 109.5 degrees apart. There's no such thing as next to versus across from. So the big takeaway is tetrahedral complexes can never, ever show geometrical isomerism. Period.
The other main kind of stereoisomerism is called optical isomerism, and this takes us right back to our hands. When a molecule and its mirror image can't be perfectly stacked on top of each other, just like your left and right hands, they are optical isomers. And we have a special name for this pair. We call them enantiomers.
So how do you actually spot them? Well, it's a mental exercise. First, you draw the molecule. Then you imagine what its reflection would look like in a mirror. And finally, the tricky part. You try to mentally spin and move that reflection to see if you can make it sit perfectly on top of the original molecule. If you can't make them line up, then congratulations, you've just found a pair of enantiomers. Okay. Whew. We have covered a lot of ground. So let's bring it all together into one powerful tool, something you can use to figure out any kind of isomer you come across. Think of this as your master checklist. When you're given 2 compounds, start with step 1. Ask yourself, is the basic way the atoms are connected to each other different? If the answer is yes, you know you're dealing with a structural isomer. Then you just gotta narrow it down. Is it an ion-ligand swap? That's ionization. Is there an ambidentate ligand? That's linkage. Or are 2 complex ions trading parts? Coordination. But if the connections are the same, you go down the other path to step 2. It has to be a stereoisomer. Then you ask, is it about a cis versus trans arrangement? That's geometrical. Or is it a non-superimposable mirror image? That's optical. This checklist breaks the whole thing down beautifully.
So there you have it. You've gone from a puzzling chemical identity crisis to having a whole systematic framework for cracking the case. So, with these tools in your pocket, what other complex chemical mysteries are you ready to go out and solve?